All right, welcome ladies and gentlemen. This is video number 1 in our acid-base unit. In this video, I'm going to be going over acid-base definitions, dissociation reactions, and these things called polyprotic acids. What are they, and how can we write reactions for them? So first up, definitions for acids and bases. In Regents, you saw the Rxns definitions, that acids produce hydrogen ions in solution, bases produce hydroxide ions in solution. And you also hopefully saw the Bronsted-Lowry definition, that acids are things that are proton donors, and bases are things that are proton acceptors. So, Arrhenius is garbage. We are not going to be using that at all. It's a very limiting definition, actually. There's a lot of things that behave as acids and bases that actually don't fit this definition. Instead, we're going to go with our Bronsted-Lowry definition because this is a much broader definition. Acids are things that donate protons. Protons are really just H+, because that's all H+ is. Hydrogen only has one proton in its nucleus. The most common isotope has 0 neutrons. And if it's the hydrogen ion, it would have lost its 1 electron to have 0 electrons. So really, H+ is just a floating proton. So we need to get really comfortable with this synonym that proton means H+ in acid-base chemistry, because it's often talked about interchangeably. Now, acids are proton donors, which means that they're things that are capable of giving away a proton, right? They start with the H+, but then they can give it away. They can donate it to something else. Bases, well, the opposite of a donor is an acceptor. So we say that bases are things that are proton acceptors. But I really don't like this word acceptor, even though it's the word that's used, because it sounds really, really passive. It sounds like the base is just sitting there waiting for someone to bestow a proton on it, and that's actually not it at all. Bases are things that take protons. Bases are tough, they're aggressive. So a better word for bases rather than proton acceptors are proton stealers, because I think this is a much better description. It's much more active, and it's really telling you what the base is doing. A base, especially a strong base, is going to be going around looking for a hydrogen ion that it can take away from something, rather than just waiting for an acid to give it one. And that's why our strong bases are dangerous chemicals, because they'll take hydrogen ion from things that aren't really willing to donate them, sort of force them to give it up. So fundamentally, what this Bronsted-Lowry definition is all about is about proton transfer. It's about the hydrogen ion. It's about the hydrogen ion going from the acid, where it's being donated, to the base, where it's being stolen or taken. So just as an example, this is an acid-base reaction. And yes, this is an acid-base reaction, even if you're not used to it looking in quite this form. And it's all about following the hydrogen, right? Follow the H. We start, for example, this is our beginning, because these are our reactants. And we've got 1 hydrogen here with the HCl and 2 hydrogens here with the water. And then over here at the end, if we follow that hydrogen, you'll notice that we now have 0 hydrogens paired with the chloride, which sort of came from the HCl. And now we have 3 hydrogens with the H3O+, which is what the water turned into. So this shows us that, the HCl, it started with the hydrogen, but then it gave it away. So the hydrogen was transferred from the HCl to the H2O, and we wind up with this chloride and the hydronium ion. This tells us then that in this reaction, the HCl is acting as an acid because it's giving away a hydrogen, because we followed that H. And the water is actually acting as a base because it's the thing that's accepting the hydrogen. And then just another example of this, we have this reaction, the carbonate ion plus water goes to the bicarbonate ion plus hydroxide. Same idea, follow the hydrogen. There's 0 hydrogens in the carbonate ion, but there are 2 hydrogens in water. This is the beginning of our reaction, right? These 2 things. And then over here, this is the end. And what happened to the hydrogens? Well, now we have 1 hydrogen paired with this thing that actually started as carbonate and then turned into bicarbonate. And now our water got turned into hydroxide, where there's only 1 hydrogen. So now what's happening with the hydrogen? Well, in this case, the hydrogen is being transferred from the water to the bicarbonate, because the water starts with 2 and it ends with 1. The carbonate starts with 0, it ends with 1. So in this reaction, the water is acting as an acid, a proton donor, and the carbonate is acting as a base. And I guarantee you that you've never seen carbonate acting as a base before in Regents chemistry, because you're like, oh, but it doesn't have hydroxide in it. It can't be a base. False. False. Bases are proton acceptors. Carbonate is definitely a base, which is why we like our Bronsted-Lowry definition. So amphoterism, let's talk about this because you probably noticed in that last example that water was acting as a base when it was paired with the hydrochloric acid, but was acting as an acid when it was paired with the carbonate ion. So we have a word for that, and it's amphoteric or amphoterism. Amphoteric substances are things that are capable of acting as both an acid and a base. And it essentially depends on the situation they're in. Water is a great example. Water can act as either an acid or a base, all depending on what it's paired with. If you pair water with a stronger acid, then water will behave like a base and accept a proton. But if you pair water with a stronger base, well, now water is going to act as an acid and donate a proton. Right, H2O, if it acts as an acid, right, it donates an H+, and we're going to be left with hydroxide. But if it acts as a base, then it's going to accept H+, and it's going to wind up as H3O+. Notice I'm not just adding on a hydrogen or removing a hydrogen. I'm also very mindful of charge because H is +1. So if you remove a +1 from the neutral water, you wind up with a hydroxide that has the -1 charge. But if you add the H +1 to water, which is neutral, then you wind up with the H3O+. Another example of something that is amphoteric is the bicarbonate ion, HCO3-. It can both donate a hydrogen because it has an H, so it can act as an acid, and when it acts as an acid, it gets rid of its H, it turns into the carbonate ion, and notice the charge goes down. We've lowered it because we've taken away a positive, but it can also accept a hydrogen ion, and that's it acting as a base, right? Bases are proton acceptors, proton stealers, and when it acts as a base, it would turn into carbonic acid, H2CO3. Notice that now that the charge is neutral, because I added a +1 to a -1. All right, review slide, strong versus weak acids. Absolutely none of this information is new, but oh, it's going to be super important once again. So just as a reminder, strong acids are things that dissociate completely, and you are going to definitely see me be using this abbreviation SA for strong acids. They completely transfer their protons, completely dissociate in solution, 100% dissociation. And that is shown down here in this slide, in this picture that is on the left. Notice that we start with 10 molecules. This is the strong acid, right? We start with 10 molecules of our strong acid shown here, but when you put it in water, all of it dissociates. So right here we have all ions, right? None of these are molecules. This is the complete ions, right? All H+, all A-. There are no molecules at all. Versus our weak acids, which I am going to be abbreviating as WA, these things only partly dissociate when you put them in water. And remember, and hopefully remember that, like, when we say partly dissociate, we mean really only like less than 5%. Very, very small level of dissociation, right? WA, right, approximately 5%, very, very weak. So here we're starting with 10 molecules again, but this is our weak acid. We put it in water. Notice that there's only one thing that has turned into that has completely dissociated. Now we have 9 molecules rather than no molecules whatsoever over here. So 9 molecules and ions, and we really have this big mixture of our ions, these things, and our 9 molecules, which are right here. So again, this difference in dissociation, this is going to be really, really important. Hold on just a sec. All right. Now, writing acid-base dissociation reactions. So when acids and bases are put in water, they behave a certain way, meaning basically they do what the definition tells us to do. When acids are added to water, they are going to donate their hydrogen ion to water. And we can actually write this reaction, and it's a very common thing in chemistry to write what is called the acid dissociation reaction. You might see this reaction abbreviated as Ka. That is, K refers to equilibrium, which is our next unit, but you don't need to know anything about equilibrium to actually write this reaction. Just I'm giving you a heads up now, it's called this thing Ka. So this acid dissociation reaction, HA, by the way, HA is our generic acid formula because it starts with a hydrogen ion. We know acids donate H+, and then it's just A for acid. And we're putting the H out in front to indicate that we know it's an acid. So this right here is a very generic acid dissociation reaction. So we have HA, that's the acid, plus water, and it turns into A- and H3O+. But what we're showing is that the hydrogen from the acid is being donated to the water, turning it into then the A- and H3O+. So we're showing the acid transfer, the hydrogen ion transfer. But there is a way that we can actually shorten this. We don't even need to write this huge long thing out. And it's because of the hydronium ion right here. The hydronium ion is made when you combine water and a hydrogen ion, right? That's what it comes from. And if you think of hydronium as water and H+, then suddenly you almost have the situation where water is the same on both the left and the right. And goodness, if chemists aren't lazy. So we like to sometimes remove the water completely and just shorten it up. It's almost this abbreviation in chemistry saying that H+ is understood to really be the same thing as the hydronium ion. We really do understand, and this is very much the case, that H+, we understand when we say H+, we know the hydrogen is probably not on its own. We know it's probably an aqueous solution, and therefore it's really combined with water to make hydronium, but we're lazy, so we can't be bothered to write out the subscript 3 and the 0, so we just say, it's H+, it's close enough. But if you remove the water and you use this abbreviation, which is totally valid to use, then we do have this shortening of acid dissociation reactions. HA goes to H++ A-. You're showing the acid dissociating into water, into its ions. Now, there are sort of two options about how we write this. If you have a strong acid, this reaction is going to be one way. If we have a weak acid, then the reaction is in equilibrium. And the way this is represented is simply a change in the arrow that we have. So for example, this indicates that the reaction is going in both directions versus this right here indicating that it's one way. So our stronger acid, we're going to have a lot more product, almost all product, right? All H+ and A-, no original HA. But if this is in equilibrium, then this reaction is going in both directions and you have everything. You'll have both H+, A-, and HA, which we know is definitely true. Now, base dissociation reactions, again, these can be abbreviated as KB. It just refers to base dissociation. And writing these is simply writing about what happens to a base, meaning bases are proton acceptors, so they steal protons. So let's write a reaction where you put a base in water and have it steal a proton. So that reaction would look like this. B, notice I'm not starting with an H anymore because I am talking about a base. So your base, this particular base has a neutral charge plus water. Goes to HB+. Notice I stuck that hydrogen out in front. That's important. You just turn this into an acid. So where do hydrogens go in acids? They go out in front. And I increased the charge. It went to +1 and hydroxide. So this base, right, took a hydrogen from water. So we wind up with HB+ and OH-. Now, the crucial thing about this to understand is there's no way that you can shorten this. A base has to steal a proton. That's what bases do. So you need to have the thing. You can't remove the water because you have to have the water there to show that the base is taking the hydrogen from something. There is no removal of the water. So all of our base dissociation reactions must always start by saying base plus water. You have to. You cannot shorten this. There is no way. So the water is not the same on both sides. It's water on the left and the hydroxide ion on the right. And you can't like substitute hydroxide with water. It doesn't work that way. And then just like with weak acids and strong acids, if this is a strong base, this reaction is one way. And if it's a weak base, then this reaction is in equilibrium. So again, we're going to have this double arrow indicating our weak base. And then just some examples to show you what I mean with real formulas. Write the acid dissociation reaction for acetic acid. So acetic acid is definitely a formula that I expect you to know at this point in the year. It is one of our most common weak bases along with hydrofluoric acid. But if you're having trouble coming up with it off the top of your head, this is related to the acetate ion. And surely we know what the formula for the acetate ion is. Yes, of course we did, because Mrs. Julian gave us that list of things to memorize on the very first day of school. And of course we have all of that memorized now, right? Right? Well, if we don't, then we need to start memorizing it now, because yeah, we absolutely need to know our ions and our strong acids in this unit. So the acetate ion, which we obviously have memorized, is C2H3O2-. Acetic acid comes from the acetate ion. So that's the acetate ion, but I want to turn it into an acid, so what do? I add H+. Well, where do I add H+? Well, you add it out in front, because that's where acidic hydrogens go, HC2H3O2. And by the way, if y'all ever try to tell me that acetic acid is C2H4O2, you are going to lose points faster than you can say red pen, because no, that is not the formula for acetic acid. The acidic hydrogen has to go out in front. It has to. That's how we write acid formulas. If you put the hydrogen in the middle, you are saying it is not an acidic hydrogen. That is not true. I don't know what C2H4O2 is, but I sure as heck know that it is not acetic acid. You will stick your acidic hydrogen out in front. If you don't, you will absolutely lose points. You will not win that argument with me, so we're going to get in that good habit right now. So, okay, we know we're going to start with the C2H3O2. And if I want to do an acid dissociation reaction, say I'm putting it in water, what do acids do? They donate their protons. So I'm going to have my acetic acid. I'm going to use a double arrow because this is a weak acid. Donate the proton to the water. The water is going to turn into H3O+. And what am I left with from acetic acid? I'm left with the acetate ion, C2H3O2-. And I also put up here the other version, the shortened version. They're absolutely both correct. 100% correct on both of them. You can just simply remove the water and just say acetic acid goes to H+ plus the acetate ion. Next up is write the base dissociation reaction for ammonia and H3. You need to memorize ammonia now. This is easily our most common weak base. More than that, it is representative of a whole class of weak bases that are nitrogen-based. No pun intended. So we really want to know NH3. NH3 is ammonia. It's not ammonium, which you've already memorized, because you should know that ammonium is NH4+. So this is the base. This is a base dissociation reaction. So we want to have, you have to start with your base plus water. Remember, there's no shortening that up. This is a weak base. So I'm going to use the double arrow. And what do bases do? Bases accept protons. Bases steal protons. So now the ammonia is going to steal a hydrogen from water. Now when we write nitrogen bases, of which this is obviously one, the rules are slightly different about the thing that they turn into. We pretty generally write the additional hydrogen at the end of the formula, like ammonia, NH4+. Notice that you never see ammonia as NH3+. That's not how it's shown. Our nitrogen bases, we put the additional hydrogen at the end. So if you ever see anything that ends in like NH2+, that's a sign that it's coming from, that it had come from a nitrogen base. So we have the NH4+, and then what's the other product? Well, the water donated a hydrogen, so it turned into hydroxide, right? It got rid of one of its H's and turned it into hydroxide. So that right there is the base dissociation reaction. And then lastly, polyprotic acids. Well, what does poly mean? Poly means many. What does protic mean? It refers to protons. So polyprotic acid is very simply an acid that has more than one protonizable proton. another way of saying ionizable. Basically summarizing, multiple H's. There are going to be multiple hydrogens that are out in front, like sulfuric acid, H2SO4, or phosphoric acid, H3PO4. These would be polyprotic acids. Hydrochloric acid would be a monoprotic acid, only one protonizable proton. That would be HCl, right? Only one H out in front. And the key thing that I want to make about polyprotic acids is that only one proton is going to be removed from the acid at a time. Sulfuric acid does not lose both of its protons at once. It's actually a stepwise process. And as an example, we're going to walk through this process for sulfurous acid. So sulfurous acid is based on sulfuric acid, which is H2SO4. But the suffix OUS means one less oxygen. So sulfurous acid is actually H2SO3 rather than H2SO4. And this is a weak acid. Sulfuric acid is a strong acid, but sulfurous acid is a weak acid. And if we want to write the dissociations, there are actually going to be two of them. And notice they're called Ka1 and Ka2, literally for removing the first proton and then for removing the second proton. So for removing the first proton, and I'm going to write out the full version, I'm going to add this to water. What do acids do? This is weak acid. Acids donate protons. But polyprotic acids only donate one proton at a time. So I'm only going to take one of its hydrogens away. So I'm going to be left with HSO3 minus. Notice the charge. I removed one positive from a neutral, so now it's -1. And I'm going to stick that extra proton on water, turning it into the hydronium ion. Then, for the second acid dissociation reaction for sulfurous acid, now I'm starting not with H2SO3, now I'm starting with HSO3 minus. So the product from that first one is actually now the reactant in the second step. Again, that's what I mean when I say stepwise. It occurs one step at a time. Same idea, plus water. What do acids do? They donate protons. So now the bisulfite ion, which is what this is called, is going to donate its one remaining proton to water. It's going to be left as the sulfite ion, SO3 2 minus. Again, notice I dropped the charge down because I removed an H plus, and again plus H3O plus. And that's going to be the stepwise dissociation. So in class, we're going to be practicing on definitions and acid dissociation reactions and base dissociation reactions.